Now this is a long story, but to try to give an introductory gist, why the Pauli exclusion principle is wrong, we could just look at the helium atom. We'll find that the helium atom has two measured ionization energies, approximately 24.6 electron volts, that's the first one, and the second one's about 54.4. And we're going to see that to suggest that initially both electrons have the same energy is not consistent with conservation of energy. For example, if you look in any textbook where they actually give the energy levels of helium, or go on the web, that's what everyone does these days, and look for energy level diagrams of helium, it'll show that initially both electrons are 24.6 electron volts. The problem with this model is, all right, I can do an energy balance. I mean, basically chemical equations are little energy balances if applied to the ionization of an atom. So we start with helium as an atom. We add 24.6 electron volts. Now we have helium ion, and we have a free electron with no energy. And the helium ion actually has an electron at minus 54.4 electron volts. So on the before ionization side, we have 24.6 electron volts of energy and a helium atom. At the end, we have a helium atom at minus 54.4 and a free electron at 0. So the question is, does the energy balance on the two sides? And the answer is no, because on one side we started off at a net energy of 0. We had an electron at minus 24.6 and a photon at 24.6. There's that to 0. And at the end we have a free electron and another electron at minus 54.4. Write it down, look at it, and you realize, gee, the second electron fell in energy. If they were both at 24.6, the second electron fell 29.9 electron volts during the process, or 29.8. When an electron falls in energy, you have to account for where the energy went. Normally, we say a photon came out. And you say, but there is no photon of 29.9 electron volts that leaves the helium atom during the ionization process. And if that doesn't, explain where the obvious difficulty lies in making the energy balance and the Pauli exclusion principle agree, because the Pauli exclusion principle basically says if you have two electrons in an atom, they're identical in all respects, all state properties, including energy. So let's look at it this way. If I start with a helium ion, it's got one electron at minus 54.4 electron volts. I now give it an electron, because we know ions want to bind electrons, they can become an atom again. At the end of that process, supposedly both electrons are back at the ground state, which is at minus 24.6, each of them. All right, when the actual electron capture process takes place, we know that there's a photon emitted of about 24.6 electron volts. So that accounts for it. Free electron gets bound, it gets bound at a state of minus 24.6 electron volts. Okay, it gives up a photon, so those two balance, no energy is lost or gained by the universe. But now we have the problem of the original electron is at minus 54.4. Where does it get 29.9 electron volts to hop back up to the energy level required for the Pauli exclusion principle to work? And we're going to discover that quantum mechanics doesn't explain this obvious difficulty with making the energy balance in the universe at the beginning and end of the ionization process or during the electron capture process. And therein lies the nub of what we're going to talk about in the next few episodes of this